News anchors read it in a flat voice. Another strange headline about space, another distant world with an impossible name. K2-18b may host signs of life, the caption says. Most people scroll past. But somewhere behind that single line of text, a 6.5-meter mirror floating far beyond the moon caught whispers of alien chemistry, filtered through the thin glow of a distant red star. In those faint fingerprints of light, some scientists think they see something extraordinary. Not ruins of a civilization, not radio signals, just a smell. The possible scent of life drifting in the clouds of an invisible ocean world 120 light-years away. Tonight, we're going to that world. We'll dive through its hydrogen skies, swim its black oceans, and stand in the middle of the scientific storm it has unleashed. Because if what some astronomers think they've seen on K2-18b is real, it could be the first time in human history that we detect life beyond Earth, not by seeing it, but by reading its chemistry across the void. First, let's find this planet. K2-18b orbits a small, cool red dwarf star in the constellation Leo, invisible to the naked eye. That star, K2-18, is about half the mass and radius of our Sun, glowing a deep orange-red in the dark. From Earth, the whole system is about 120 to 124 light-years away, close by galactic standards, but unimaginably far for us. Now look closer at the planet itself. K2-18b is big, around 2.6 times the radius of Earth and roughly 812 times our planet's mass. It circles its star once every 33 days at a distance of about 0.14 AU, less than half the distance between Mercury and the Sun. Yet because K2-18 is so dim and cool, K2-18b receives about the same amount of starlight that Earth does. On paper, that puts the planet right in the so-called habitable zone, the region around a star where liquid water could exist. But this is no second Earth. With its low density, K2-18b probably isn't a rocky world with thin air and continents. It's something stranger, a sub-Neptune, a halfway point between a super-Earth and an ice giant, wrapped in a thick envelope of hydrogen and helium. That combination, Earth-like temperature but Neptune-like structure, led scientists to wonder, could there be an ocean hidden beneath that hydrogen sky? A deep, dark, global sea, warm enough for chemistry, shielded beneath clouds and gas. This idea gave birth to a new class of hypothetical planets, Hycean worlds, ocean planets with hydrogen-rich atmospheres, potentially friendly to life. If Hycean planets exist, they could be the most common abodes for life in the galaxy. They're easier for telescopes to study than tiny Earth-sized rocks, and theory suggests they might have stable oceans for billions of years. K2-18b, sitting right in its star's habitable zone, quickly became the poster child for this new family of worlds. But ideas aren't enough in science. You need data. And to read the atmosphere of a world 120 light-years away, you need something very special. Enter the James Webb Space Telescope. When K2-18b passes in front of its star, a thin sliver of starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different colors of that light. By splitting the star's light into a spectrum and measuring tiny dips, Webb can work backwards to figure out what the planet's air is made of. In 2023, Webb pointed its instruments, NIRIS, NIARSPEC and MIRI, at K2-18b during several transits. What came back was not just a curve on a graph, but a chemical fingerprint, unlike anything we've seen before on a temperate exoplanet. The first big result, methane and carbon dioxide. Webb's spectra showed strong signatures of both gases in K2-18b's atmosphere, while ammonia seemed depleted. That combination, methane plus carbon dioxide in a hydrogen-rich atmosphere with little ammonia, fits predictions for a Hycean world with an ocean underneath. On our own planet, methane is produced by both geology and biology, volcanoes, hydrothermal vents, cows, microbes. Carbon dioxide is even more universal. So seeing CH4 and CO2 on K2-18b doesn't prove anything, but it tells us carbon chemistry is active, and this world is not sterile. Still, what really lit the fuse wasn't methane or carbon dioxide. It was a rumor at first, a whispered word in conference halls, then a preprint, then headlines screaming across the internet. A third molecule might be lurking in those spectra, a molecule with a very particular story on Earth, dimethyl sulfide, DMS. On our planet, this gas is almost exclusively produced by life, mostly by tiny marine organisms called phytoplankton, which release it as they grow and die. DMS drifts into our atmosphere, seeds clouds, and helps regulate climate. It is, in a very literal sense, the smell of a living ocean. When the Cambridge team analyzed Webb's data, they found that adding dimethyl sulfide, or a related molecule called DMDS, made the observed spectrum fit significantly better. The signal wasn't strong enough to declare a discovery, but it hovered at the edge of statistical significance, around 3 sigma. Tempting but not conclusive. Across the world, headlines exploded. Strongest evidence of life beyond the solar system. Alien ocean world may be teeming with life. But scientists were more careful. Even the authors of the study labeled the detection tentative, emphasizing the need for more data. And other research groups disagreed entirely. Reanalyses of the same Webb data argued that the DMS signal may vanish under stricter scrutiny, contaminated by noise, or confused with other complex molecules. So what do we actually know? We know K2-18b has methane and carbon dioxide. We know ammonia appears depleted. We know some analyses find hints of DMS, while others see nothing convincing. This is a mystery in progress, a scientific cliffhanger. But for a moment, imagine the optimistic scenario is right. Close your eyes and fall through that hydrogen sky. The red light of K2-18 fades into a dim glow as clouds thicken around you. Temperature rises, pressure rises. Eventually, the gas stops being air and becomes something else. Somewhere below there could be a boundary, not a rocky surface like Earth, but a transition into a dense global ocean, perhaps hundreds of kilometers deep. A churning sea warmed by the greenhouse effect of hydrogen and methane. In that kind of ocean, life, if it exists, would almost certainly be marine. Imagine something like phytoplankton, microscopic organisms drifting in the upper layers, feeding on faint red starlight. As they metabolize sulfur compounds, they release dimethyl sulfide into the water. Just as plankton do on Earth, currents lift that gas upward, storms mix it, lightning crackles. Eventually, the gas reaches the upper atmosphere, where Webb reads its spectral fingerprint. Could such chemistry really support life? Some geochemists think so. If K2-18b has a water-rich interior and the right mineral cycles, energy sources might exist just as they do